So when we start with your distinguishable permutations, you might remember this from Algebra 2. Distinguishable permutations say you have to take the duplicates out. And say I give you a word like noon, and I want to know how many different arrangements I can make from this word. Can anybody find another arrangement to make? Can you find one? What other? It doesn't have to be a real word, just an arrangement. No. Okay. Now I'm going to make another one. No, it's not. I changed the ends. I changed the ends around. Oh, okay. And Gio wants to make one where I change the O's. Ah. So here's our problem. These are not distinguishable. I can't tell the difference between these. So when you use letters that repeat, you have to be careful. You have to take out those duplicates. I can't count this one or this one. I have to be able to take them out of there. Alright, so here's what we do. We keep track of how many we want. In this case, we have 4 letters, 4 factorial, and we're going to take out the duplicates. So keep track of the letters that repeat and how many times they repeat. So we have 2 N's, we have 2 O's. You take these guys and you put them underneath, like this. Now, be careful when you do this. In your calculator, you have to have parentheses around this. This is a great Algebra 2 problem. But the problem is, when people put it in their calculator and they did this, it divided this and then it multiplied it. So you've got to be really careful. This is 4 factorial. Over 2 factorial is just 2 times 1, 2 times 1. So out comes a 2. This goes in here. And I'm only going to find 6 unique or distinguishable permutations for this. Because if we switch the O's, you can't tell. If we switch the N's, you can't tell. So you're only going to get 6 unique ones, 6 distinguishable ones. These are your distinguishable permutations. And they work with whatever scenario you happen to come up with. And this is a great one because I don't think anybody ever anticipates what goes into thinking about what a contractor does, building houses, setting up, landscaping. You have a building contractor planning to develop a subdivision. The subdivision is divided into 6 one-story houses, 4 two-story houses, and 2 split-level houses. How many distinguishable ways can the houses be arranged? In other words, if here's his 1-story, 2-story, and split levels, I'll go halfway up. He can't just switch these 2. You wouldn't be able to distinguish the difference. So he wants to know how many distinguishable ways can he arrange all of these houses. He's got 12 houses to arrange. So we're going to do 12 factorial over, take out your duplicates, 6 factorial, 4 factorial, 2 factorial. It gives them far less ways to arrange those, that they'll be distinguishable. In other words, when you go into a development, you don't want to see all the same pattern repeat. You don't want to see all the same houses together. You want a variety. You want a mixture. Otherwise, you go in and you say, it feels like I'm living in a separate place. Everybody's arranged like this. And so you want a little bit of variety. These are how many different ways that they'll be able to do this. Now, it cuts down on how many different permutations you have. So we can come up with 13,860 different ways to set this up. So imagine what a contractor goes through when they're trying to arrange a subdivision of houses. It never seems like that would be possible, but it really is if you think about it. Okay? So I want you guys to try the next one. These are your distinguishable permutations. They can be used in this grouping as well. You're going to be amazed at the number for this one. They're arranging trees. Who would have thought? So anybody come up with a number? I hear it. 77 million. 520. Is that it? 520. It's a lot of different ways. Everybody get this one? So we have 6 oak trees, 9 maple trees, and 5 poplar trees. Altogether, he has 20 different trees to arrange. So 20 factorial over, take out your duplicates. 6 factorial, 9 factorial, 5 factorial. Take those duplicates out of there. And if you do them in your calculator, make sure you put parentheses around your denominator. There's a lot of different ways. Okay. From here, we're going to take a look at your combinations. Now, combinations say, I don't care about the order. Committees, teams, sets, subsets, subdivisions. Those do not care what order you sit in. Now, if I had 3 people, A, B, C, and I wanted to pick 2 people, a president and a vice president, to send to the office, how many different ways can I do that? Permutations. How many ways can I send 2 people to the office? To be a president or a vice president? 6. So you said 2 people, you have 3 to choose from, then 2. 6, right? You have AC, you have AB, you have BC, you have BA, and you have a CA and CB. And you have 6 unique ways to send a president and a vice president to the office, right? Now, I want to change that. I want to send a committee of 2. Order doesn't matter. So, if I send AC, is CA any different? No, they're the same. They'd be the same committee, right? If I send AB, which one is that the same as? BA. And if I send BC, that's the same as CB. So now instead of having 6 different ways, I only have 3 different ways to send my committee. Combinations, 3 things, 2 at a time. Don't use their formula. Do it like you do permutations, but we take out the duplicates. We do 3 things, 2 at a time, 3 times 2, and divide by whatever this is, factorial. And out comes the 2. See it? It's the easiest way to look at this. Combinations have less ways than the permutation because your order doesn't matter. Your AC and your CA are the same committee. Your AC was president, vice president. Your CA was president, vice president. But in a committee, it doesn't matter. Well, yeah, because 2 factorial is the same as 2 times 1. Well, if it's a big number, then you can't cancel out a factorial. Yeah, like say it's a combination of 5 things 2 at a time. Start like this. 5 times 4 over 2 times 1. 2 factorial. Whatever this is. Start like you would do your permutation and take out your duplicates like we do the distinguishable ones. It works better than using their formula. Or you can even use your calculator. If you did 5C3, you're going to do it 3 times. 5, 4, 3, and then 3 factorial, 2, 1. And then you can take out your duplicates in here. Okay. 5C3, by the way, and 5C2, when these add up to the same number as this one, they give you the same combination because your order doesn't matter. This is going to lead us into all the things you did with Bernoulli's when you made those C things and you put the success, the failure. This is going to kind of lead us into that. Now, your combination says to you the order doesn't matter. So here we have a State Department of Transportation's plan to develop a new section of your highway, and they received 16 bids for the project. The state plans to hire 4 of them. How many different combinations? Now, be careful because even though they use the word different, they use the word combinations. They can sometimes say different arrangements for a permutation, different combinations, different committees, different teams for a combination one. How many different combinations of 4 companies can be selected from these 16 bidding companies? Well, do they care about what order they hire them in? Nope. So combinations, how many do we have to choose from? 16. And how many do we want? 4. So this one says combinations of 16, 4 at a time. If you work it out the long way, you go down 4 places and then you do 4 factorial. And if you want, you can reduce this or you can put it in your calculator, whatever you want. It's probably easy to reduce. And then just multiply the top if you want to work it out. Or you can put 16C4 in your calculator. And you're going to come out with 1,820 different combinations of 4 bidding companies out of the 16. I think this gives you a better respect for what these people actually go through when they're choosing things, right? If I choose this one with this one, and this one with this one, and this one with that one, and he's got 4 to put together, it's a lot. Okay, you guys try the next one. Try this one. You try this. So what'd you get? How many do you have to choose from? 16. What'd you get? 560. You want 3 of these. Okay, you want 3-person advisory committees, 560. Agreed? Okay. All right, tomorrow we're going to finish this up, and then we'll be done with this first basic chapter of probability before we move on to the next one.